Hi everyone, welcome to part 2 of our 3-part GPT workshop. In part 1, we talk about word embeddings and how language is represented in neural networks. Today's part 2, we're going to talk about GPT, the architecture that powers it, and the original context it was created. And in part 3, we'll use that knowledge of how GPT works in order to write it in PyTorch from scratch. Okay, let's get started. So first, a little bit of context. Let's talk about what GPT stands for. So GPT stands for generative pre-trained transformer. So generative makes sense because we generate text. Pre-trained makes sense because when we use these models, they're already trained for us, and they can be fine-tuned for downstream tasks. And transformer is a keyword we're interested in today. The transformer refers to the architecture on which GPT is based. So what is a transformer? The transformer was invented in 2017 by researchers at Google in a paper called Attention is All You Need. So let's refer to that paper right now. Here's that paper. The title is Attention is All You Need. The key idea of this paper is that there's this concept called attention, and it's all you need, meaning you don't need recurrence or a lot of what people were using before transformers in order to make a really good language model. So let's take a look at the abstract real quick. Essentially, the important parts are that the model was originally trained in this paper for machine translation. So we see English to German and English to French. So basically what this paper is about is a model architecture to perform machine translation or translation between two different languages. And they find in this paper that this architecture performs exceptionally well at this task. Now what happens after 2017? You can see that this paper was published in 2017. What happened afterwards is that people realized that this model architecture was good not just at machine translation, but all general sequence-to-sequence tasks. And so here you see the term sequence transduction. This just means converting a sequence to another sequence or possibly any other form. So taking in the sequence as an input. And since language is just a sequence of words, this works really well for natural language processing. But you can also see this used for music, which is or audio, which is like a sequence of like samples, or like video, which is a sequence of images. Okay, so there's a little bit of background here. Before transformers, the model primarily used for language tasks, it's called the recurrent neural network. Basically, these networks are kind of like your standard feed-forward neural network, except when they predict the output, they also append that back to the input and have a hidden state that keeps track of essentially all of the states that came before it. But it's not extremely important to dive super deep into recurrent neural networks because today that paradigm has largely shifted from recurrence to transformers. So while still relevant, we're going to be focusing on transformers today because they perform so well and have been largely responsible for the success in the past 5 years or so in NLP and other sequence tasks. And basically the idea is that in recurrent neural networks, there's an idea proposed called attention. And this idea of attention started to be used more and more in recurrent neural networks until at the publication of this paper, they discovered that attention is all you need. You can eliminate the recurrence entirely and just use attention. Okay, so let's look at the model architecture. Here we have our model architecture diagram. And it looks really complicated, but we're going to break this all down, and it actually turns out to be pretty simple. And the key equation that we're going to start with is here. So let's take a look. Essentially, in a transformer, we're going to use our previous paradigm of embedding words into a vector space. So what that means is that we have a sentence like, for example, the dog jumped. This is an English sentence. And recall that we can assign a vector per word. For example, we can say the is a vector that's like 0.3, 0.7, negative 0.1, 1.2, up to some number of elements, right? This might be any number of elements long, which we'll call d. So d is the length of the vector that represents each word. And the word dog will have another vector, and the word jumped will have another vector. So every word is represented as a d-dimensional vector. And what we'll do is to represent the sentence, we'll just essentially concatenate them. Or not necessarily concatenate, but stack them, like one on top of each other to form a matrix. So this particular sentence, dog jumped, may be represented as this matrix. This 3 by d dimensional matrix may represent the sentence, the dog jumped. So this is our input, and we call this input x. These are also known as embeddings because they embed language into a vector space. Okay, so we have our input x, which is an embedding, and our goal is to produce an output y. And this y, or we can write it as this, it's up to you. But y is essentially going to be our probability of predicting each next word. And here, I'll write a lowercase y here to denote like a vector of probabilities among words. So y is going to be like this. If we have a total vocabulary, right? Like let's say we have the word like bee, dog, cat, tree, and so on. We have every word in the English dictionary in this vector. We'll have a probability for each word. And the idea is that given the text like X, right? So the dog jumped over. What is the most likely word to follow, to follow this sentence? And that probability, that word might be over. So like, let's say this is over, right? The probability of the word following the sentence might be pretty low, like let's say 0.05. And B doesn't make much sense either, so let's make this like 0.001, and so on. And the probability of over might be really high, like 0.8, whereas the probability of other words might not be as high. So the idea is that given a sentence, we want to predict the probability for each word in the vocabulary of that word following the input sentence. So this is our framework. We have an input embedding x, and we want an output probability distribution y. It's a probability distribution because if you recall in statistics, all of these elements will sum to 1. And so every element in this vector denotes the probability that that word follows the input sentence. And so this is a discrete probability distribution. Okay, so we have our input, the transformer, x. And we're going to generate an output, y, through the transformer. So how does this transformer work? This transformer works mostly through a sequence of transformer blocks. And inside each transformer block is what is known as attention. So it looks like this. A transformer is a sequence of like transformer blocks. I'll say T block just for brevity. So first, like, you'll have like this first transformer block, then another transformer block, and so on. And within the transformer blocks, within a transformer block, you have what's called attention. And you also have a feed-forward neural network. So this is the vanilla neural network that you all are familiar with. Okay, so let's first start with attention, and then we'll come back to the transformer block as a larger building block. So what is attention? What is attention? So the idea of attention is that language has to be interpreted in context. So for example, like if I use the sentence like I took a walk by the riverbank. And I checked my bank account balance. The term bank in both of these sentences mean different things. The first refers to a riverbank, and the second refers to a financial bank. And so it doesn't really make sense to use just the vector that's associated with bank. We need to consider the context, meaning the other words surrounding the word bank in the sentence, in order to infer what the word bank means in that sentence. So the idea of tension is that we need to associate different scores between words in the same sentence. Right? So essentially what we'll have is like if we have a sentence like the dog jumped over the fence, we'll write this sentence down also, like the dog jumped over the fence. And we'll create what's called an attention matrix, a self-attention matrix. And along the diagonal might be some value, like let's just say like 0.1 or something like that. And so on, along the diagonal. And the idea is that the word jumped, right, might have an attention score with fence. Or like over might have a like high attention score with the fence. Because essentially what's happening is that we want to like give an association between each word and every other word in the sentence. So like for every pair of words in the sentence, we want to give that an attention score. Attention tells what the model will to focus on, essentially. So since the dog is jumping over the fence, we might want to look at like the word over and fence, right? And that might have a high attention score. So if we see like over here and fence here, we might want fence to have a high attention score. So like 0.5 or something like that. Whereas over and this word the don't have a very high attention score because like the and over are not related actually at this part of the sentence. So over and the here might have a higher attention score, but this word over does not really have much relationship to this word the. And so this might have a very low attention score. And we'll make a matrix that represents the attention scores of the input. So how exactly do we do this? The paper gives us this equation. Attention equals softmax of qk transpose over a square root of dk times v. So what does that mean? They don't elaborate in the paper, but essentially what they're doing is they're taking a weight matrix. So if I have the input x, then I can define a weight matrix such that when x is multiplied by it, it produces an output q. So x is a matrix and WQ is a weight matrix. And same goes for the others, K and V. Okay, so what are we doing here? We're essentially changing the dimensions of the matrix and reinterpreting x as what are called keys, queries, and values. So Q stands for query, K stands for key, and V stands for value. So what does this mean? Essentially, the idea here is that when you perform like a Google search, as an analogy, you'll have some kind of search term in the search bar, right? So like, what's a good example? Like, let's say cats. And there might be a picture, there might be an article that talks about like 10 different cats. In Gainesville. And this is the title of the web page. And there might also be like a large body of in the web page, like of the description of like everything in the page, or like a lot more text within the page, whereas this is like the title. So the idea is that this is what we call the query. This is what we call the key. And this is what we call the value. So the query is what's being searched for. The key is like essentially a match. And so you have a set of matches, a set of keys. And the value is essentially like the content of that match. Okay, so that's an analogy for Q, K, and V. Let's take a look at the dimensions of these matrices. So X has, let's say, L words. So if X has a length of L, then it will be an L by D matrix. So in mathematical notation, we can write it's a real matrix of L by D. So that means that it has L rows and D columns. And WQ, WK, and WV will also have dimensions, so I'll write them here. WQ will have the dimension of L by DQ. WK will have the dimension of L by DK. And WV will have the dimension of L by DV. And so what will happen is that, not L, D by each of the others. Because when you multiply X by these weight matrices, they'll generate the L by D whatever equivalence. Okay, so what's happening here? If we consider like matrix multiplication between like X and WQ, if we consider the dimensions, we have an L by D matrix multiplying a D by DQ matrix. And when you multiply two matrices together, essentially this middle dimension has to match. And then the resulting matrix will have only the outer dimensions. So if this is X and this is WQ, then the output, which is Q, is going to have these dimensions. So what's happened here? If we look at like X as a list of vectors, so each row in this embedding matrix represents the embedding of a word. Then what we've done is we've gone from an L by D matrix to an L by DQ matrix. So what we've done is changed the dimensions, like how many columns are in the matrix. So this might be like, for example, a narrower matrix. or it could be a wider matrix, or it could be the same size matrix if we'd like. Right, so this is going to be like Q. So the dimensions are like every row will still represent like a query, but the query's dimensionality doesn't have to be the same as the input embeddings. So this will be D, and this will be DQ. And we do the same thing for keys and values. So we'll end up with like a queries matrix, a keys matrix, and a values matrix. And then we're going to perform this operation. First, we're going to take Q and multiply by the transpose of K. So what does this do? Let's consider Q, and let's consider K. So K has a dimensionality of L by dq. And K has a dimensionality of L by dk. But if we transpose it, then the dimensionality will be reversed, dk by L. And so now we have dk rows and L columns. So we have dk rows and L columns. And remember that in order to perform this matrix multiplication, we need the inner dimensions to match. So we have Q and K transpose, and the dimensionality of Q is going to be L by dq, and the dimensionality of K is going to be L by dk, but the dimensionality of K transpose will be that flipped, so dk by L. And in order for this matrix multiplication to be possible, we need the inner dimensions to match. And so we have this constraint actually, that dq is equal to dk. So whenever you set dq and dk, they actually have to be equal in order to perform this operation. And our output will be an L by L matrix. Okay, so this will be, the result of this will be a square matrix. And this will be the unnormalized attention scores between the keys and the queries. So the idea is that like when you perform any kind of search, like for example, this Google search, you want to like get keys that are similar to queries. And the way that you get that for vectors is you perform a dot product. So if the dot product between two vectors is high, that essentially implies that they're similar. So like as an example, right, if we have a vector in 2 dimensions, and like this is like the vector for the word great, then we might expect the vector for the word good to be like very similar to great, except maybe a little bit smaller magnitude. And so the dot product between great and good may be very high. And like we can consider, for example, the like normalized dot product, which we also call cosine similarity. Oops. So if we divide the dot product of great and good by the magnitude of each respective vector, we'll get some value between -1 and 1, and we expect this to be actually like pretty close to 1 because the vectors are very similar. And as an alternative example, the vector bad might be in the other direction. And so the cosine similarity or normalized dot product between great and bad might be closer to -1 instead. And so the idea is that by taking a dot product between vectors, we'll get a similarity score. And by taking a dot product between a row of the query matrix and a column of the keys matrix, we'll get some score for how similar they are in this element here. And that's the same for the second query and the first key here, and so on for the rest of the matrix. Okay, so now we have unnormalized attention scores. What we would like is we would like to enforce the constraint that the sum along each row is 1. So how do we do that? We do that with a softmax. Oh, and I should mention that they have a scaling factor, square root of dk, in order to prevent everything inside from being like very large. And this is important for the softmax actually. So first I'll explain the softmax, and then I'll explain this scaling factor. So softmax is an operation that takes in a vector like, let's say the vector is 0.1, 0.2, negative 0.3. So the sum of these elements is not 1. In fact, the sum of these elements is 0. So what the softmax does is it converts this vector into a new vector. And it's going to be the operation is defined as follows. For every element, if the input vector is like x1, x2, and x3, then the output will be essentially xi over the sum across all the other elements, xj, except we'll exponentiate both the numerator and the denominator. And the exponentiation essentially pushes values to be more farther from each other. So it like essentially like if you have a value that's like negative, that's like 0.4 and 0.6. When you take e to the power of 0.4 and e to the power of 0.6, like e to the power of 0.6 will get like larger relative to e to the power of 0.4. Okay, so here's the softmax operation. So the output of this vector will be like e to the power of 0.1 over the sum of like e to the power of 0.1 plus e to the power of 0.2 plus e to the power of 0.3, negative 0.3. And same for this vector. And same for this vector. Element. Okay, so that's the softmax. The result will be a vector, a vector whose elements all sum to 1. So if you add these, certainly you'll have the same value on the numerator and the denominator, and so the sum is 1. And what softmax means for a matrix is applying the softmax for each row. So if we're softmaxing this matrix, we're softmaxing for this row. So all of this row's elements will sum to 1. All of this row's elements will sum to 1, and so on for every row of the matrix. And there's also the scaling factor, square root of dk. What the scaling factor does is if you have like the exponential function plotted, you may notice that for like high values, e to the power of like 100 and e to the power of like e to the power of 99. So this is 99 on the x-axis and 100 on the x-axis. Then e to the power of 100 and e to the 99 have like a huge difference. Like e to the power of 100 minus e to the power of 99 is huge, right? This is like e to the power 99 times e minus 1. And since e is like, I think 1.7, let me double check that. Sorry, 2.7. Then e to the power of, e minus 1 is going to be like 1.7, and this will be like around like 1.7, like 2.7 to the power of 99 times 1.7, which is like an enormous number. Whereas if you have like e to the power of 1, like down here, right? and e to the power of 2, this is only going to be like e times e minus 1, which is like 2 to the 0.7 times 1.7, and this is like way smaller than that. But the difference on the x-axis is the same. So we don't want a gigantic difference in the y-axis. And so the scaling factor dividing by the square root of dk just makes everything smaller so that we don't get into this region, and we stay in this region instead. And there's some more mathematical explanation about variance in the paper. So essentially, like, they assume that every element of the vector has a mean of 0 and a standard deviation of 1. And if you scale by the square root of dk, then I think they mentioned in the paper. So if every element of q and k have mean 0 and variance 1, then the dot product is like the sum of the products of each element pairwise, and the variance will be dk. So if you scale by the square root of dk, which is standard deviation, then you should also have a variance back to 1. Okay, great. So that's the softmax of all of these, all this. And we're finally going to multiply it by a values matrix, which is just like our queries and keys matrix. So every row of the values matrix will be a value vector extracted from the input. Okay, and this is the attention operation. So attention of x is going to be this. Great, so that's actually the main equation used in transformers. And there's just a few more like parts that we should consider. So if we refer back to the paper, we see our attention in a diagram, and we'll also see multi-head attention diagram. So what are these two? So this one we just talked about, except you also see this element of a mask. We also have multiple heads of attention. Okay, so let's first talk about the mask. What is masking? So the idea of masking is that we want transformers to predict the next word in like an input sequence, the word that follows an input sequence. And so during training, we don't want the transformer to have access to like the next words in the input sequence, because that's a form of cheating, and it won't have access to those words when we actually run inference. So for example, if I have the sentence like the dog jumped over the fence, we don't want the transformer to be able to see the words over the fence when it's predicting the word over. And so what we need to do is we need to actually mask the attention scores. If these are attention scores like Q, K transpose, or square root of dk, and I'll say SM for softmax, then what we'll do is we'll take this diagonal and we'll zero out everything above the diagonal and preserve all of the elements below it. So all of these elements will be preserved, and all of the elements above the diagonal will be set to 0. And you can verify mathematically that this has the effect that we want. It's also there's also a technicality that this is often applied before the softmax, and if you apply this masking before the softmax, you actually set everything above the diagonal to negative infinity. So you'll first compute this value in the matrix, and then you'll set every value above the diagonal to negative infinity, because when you take the softmax, you'll get e to the power of negative infinity over all the other elements, and e to the power of negative infinity is like essentially like 0. right? Okay, so that's masking. The idea is to prevent the model from cheating by using like context to the right of the current token. Now we want to talk about multi-head attention. And this is actually a very simple modification of single-head attention, which we've been doing. So the idea of multi-head attention is that their language has multiple aspects like within the same sentence. So for example, if I have the text, I took a walk at the park, in the park at noon. There's actually a couple of aspects of this sentence. So one is spatial. Where did I take the walk? It's at the park. Right, spatial. And another is temporal. When did I take the walk? It's at noon. And the idea is that we want our model to be able to attend to different aspects of language. And so we'll train like an attention layer, right, for the spatial aspect of things. And we'll also train another attention layer for the temporal aspect of things. And then we'll concatenate them, right? So not like plus as an addition, but like if this is a matrix, then we'll like put the values like side by side with the other matrix. And so each of these is what we call a head. In practice, we're not able to teach the model exact semantic features like spatial or temporal features, but by creating multiple heads and concatenating them, the model is able to attend to more aspects of language at the same time. So we don't have quite as much control as we would like to, but but having multiple heads of attention tends to work better than single head attention for this general line reasoning. So there's attention and multi-head attention. Let's now take a look at the transformer block. So transformer block has multi-head attention, including possibly masked multi-head attention, and it also has this thing called add a norm. So what is that? So the idea of add a norm, these are two separate ideas. The first idea is add, and the second idea is norm. So what is add? Add actually refers to what's called a skip connection. This is also called a residual connection. And the residual connection was introduced in the paper ResNet in 2015, published in Microsoft Research by Kaiming and others. So if you want to read more about skip connections, I encourage you to reference this paper. And the idea of a skip connection is that in a feed-forward neural network, when you have like your layers, right? So here's your layer, and here's another layer, and here's another layer. You pass data through the layers, right? So here's your input X, and finally you get some output Y. It turns out that if what you do is you take this input and add it to the output of layer 1, and add that to the output of layer 2 and the output of layer 3. So what's happening is that we have like our standard, X. We might have like layer, like out equals layer 1 of X. Out equals layer 2 of out, and out equals layer 3 of out, return out, if this is our forward function in PyTorch, what we can do is we can add x, add out, and add out here. This is the add that's being referred to in the paper, and this is what's a skip or residual connection. And what happens is that by providing this other pathway, like aside from the layers, it actually smooths out the loss function. So this is like actually kind of a surprising discovery. What happens is that if you have a loss function, if this is like your parameters, and this is like your loss, then typically a loss function looks something like this. Let me draw a different one. If you initialize your weight somewhere like here, then using gradient descent, you may like end up going here, right? And predicting here, and then here, and here. And you found a loss that's a local minimum. This is what we want to prevent because there is a much lower loss right here. So what residual connections do is they smooth the loss function. After residual connections, the loss function looks something more like this. And so like, or like this. So this is inexact, but the idea is that like there are less like local minima to be trapped into if you use residual connections. So this works really well empirically. The second aspect is called layer norm. So what layer norm is a form of normalization. Basically, it prevents outputs from becoming too large. It prevents outputs from, one sec. It prevents outputs from becoming too large. So if you remember in statistics, you can normalize something by the mean and standard deviation like this. Oops, mean and say like standard deviation, like that. Layer norm does something very similar where it'll like essentially subtract the mean like element wise and divide by the standard deviation, and then also use like a couple of hyperparameters also. So I'm not going to talk too much about the exact specifics because I don't think they're terribly relevant to the transform in particular. But like if you want, you can definitely look up layer norm, and it's also like called layer normalization for in full. Normalization. And basically like this prevents the outputs from like after passing through many attention blocks, or like let's just say from if the output of a transform block is like kind of large, like the values in the elements of the matrices are really large, then layer normalization will shrink them, right, by subtracting the mean and dividing by the standard deviation to be like smaller values to work with. And so this will prevent values from like getting super large and causing like vanishing or exploding gradients to some extent. Okay, so now we have added norm, and the final thing we'll do is we'll run through a feed-forward neural network. So we have this part. So a transformer block really looks like this, like here. So we have, what does the block look like? Oops. We'll have self-attention, and then we'll have add a norm, and then we'll have a feed-forward neural network, and then we'll have add a norm again, And that's a transformer block. And the transformer is just a bunch of transformers blocks. And so on. And so that's actually like basically the majority of the transformer architecture. There's one like little thing that I should mention called positional encoding. So the problem at this point is like the model doesn't actually have any idea of position. So like if we send in like the input, Mary pet the cat, this actually to the model is equivalent to the cat pet Mary. Like the model actually doesn't really have an understanding of the order of words. It's what we call like it's like invariant to the positions of words, right? And so we need to inject some information about positions. And how do we do this? We'll just add what are called learned positional embeddings. So if this is x, then we'll just have a matrix PE with like a maximum context length. And when we get an input x, we'll just add like the first. We'll just take like the number of rows that are in x and just add element wise. So we'll have an embedding for each row essentially. So there's an embedding for the first row, an embedding for the second row, an embedding for the third row. And this just references like the first like token in the sentence, the second token in the sentence, third token, and so on, up to some kind of maximum length. Okay, so that's what we call learned positional encoding. There's also a sinusoidal positional encoding introduced in the paper here. I don't think this is terribly important. If you want, you can work through it, but to some extent, it's a little bit arbitrary. Like they use the number 10,000, like with the number 1,000 or 100,000 work also is completely possible. And they say that learned positional embeddings tend to work like quite as well. They said produce nearly identical results. And so we will be sticking with learned positional embeddings, which is this variant for simplicity. Let's look at the transformer architecture one more time. Here. And we'll see that we've essentially covered all of the relevant aspects. So here's your input embedding. Here's a transformer block, which includes multi-head attention and adding and norming. And then also a feed-forward neural network and also another add-in norm. And after a bunch of transformer blocks, we'll use a projection matrix to get to our output probability distribution. One caveat to transformers is that when they produce an output, it's actually not going to be a single vector y that I mentioned earlier. Instead, like this will be our output vector y, and this will be like a output vector for each like word before like the last word. So actually, like if we have the sentence like the dog jumped, this will still be like the probability vector for like the word following the, and this will be the probability vector for the word following dog, and then only like the last one, the last row of this matrix will be the probability vector for the word like what follows after the word jumped. Okay, so that's essentially the transformer architecture. And one more last thing, I guess. You can see that there's like two sides here. So there's like a left-hand side and there's a right-hand side. And everything in like the left-hand side is not masked, but like this is masked here. And the reason is we split this architecture into what's called an encoder and a decoder. So this is an encoder. and this is a decoder. And yeah, all the differences is like the decoder is essentially like an encoder. But with the mask. So this is that mask multi-head attention where you zero out all the elements above the diagonal. So we've seen like a little bit of difference in like use case depending on encoder and decoders. So for the task that they're doing in the paper, which is machine translation, we typically use an encoder and decoder architecture. And then for something like sentiment analysis, I'll just say essay. And this is like, sentiment analysis just means like, given some sentence, tell whether the sentiment of the sentence is like positive or negative. So like, I had a good day would have a positive sentiment, and you would want the model to predict that. This might be an encoder only model. And the last one, like GPT, is what's called a decoder only model. So actually every attention layer in GPT has a mask to prevent it from attending to to prevent backwards dependencies from being formed. So it can't cheat by like using future tokens that it won't have access to during inference. Okay, so actually like ChatGPT doesn't actually have this part here. It just has decoders, decoder blocks. Great. So yeah, that's the attention is all you need paper. That's the transformer architecture. And next, during the next part of the workshop, part 3, we'll implement this in PyTorch. And yeah, if you have any questions, feel free to message me, and see you all later.